Now we're going to continue on with the second lecture for Module 2, looking at the topics of stress and strain, continuing on with axial loading. Specifically, we're going to get into some work with Poisson's ratio, take a look at multi-axial loading and generalized Hooke's law, and then talk a little bit about dilation and bulk modulus, go through a couple of applications, some of the key and governing equations you'll be utilizing, and go through some methods for problem solving as well. So we're going to start out with Poisson's ratio. So if we take a look at this example over here in figure A, we have some materials undergoing transverse contraction when elongated under an axial load. So we're still sticking with our axial load here. So for this slender bar subjected to this axial loading, we have the following relation right here. Our strain, our epsilon sub x, is equal to our stress in the x direction divided by our modulus of elasticity. And our sigma y, our stress in the y, is equal to our stress in the z, which is 0. So we just purely have the stress acting in our x direction only and nothing happening as far as stress goes in the y and z directions. Now, this elongation in the x direction is going to be accompanied by a contraction as well in the other direction. So assuming that the material is going to be homogeneous and isentropic, so no directional dependence, we can get this following relationship here, that our epsilon y is equal to epsilon z, and this is not going to be equal to 0, but they are going to be equal to each other in the other two directions. And if you think about this in practical terms, for any of these applications, they give us a diagram. I like to pretend I'm actually going to pull, push, roll, whatever it is, the objects. You can see here up in the corner, we have this P right here. So we're going to pretend we're going to pull on that. And if that's going to elongate in that X direction, what is it going to do in the Y and Z direction? If you pull it, it stretches in. So we've seen necking occur before in some of the other examples we've talked about. So practically, what do you think is going to happen? Well, your Z and your Y are going to kind of contract in. So if it elongates in the X, it's going to force that Z and Y to contract in. Now we come down here and we can see that from Poisson's ratio, this is going to be defined as we have our negative lateral strain over our axial strain, take the absolute value of that right there. So for our lateral direction, we have our y direction right here as our lateral direction. We have our axial direction here as our x direction. So there's our x-axis right there going along there. So we have negative, in this case here, epsilon y over epsilon x, which is equal to, in the other direction here, now a lateral one here, is our z direction over our epsilon x there. And that's because our epsilon y is equal to our epsilon z right there. So we have this relationship here for Poisson's ratio. So next I want to take a look at multi-axial loading and applying generalized Hooke's law. So we can see over here in figure 2.33, we have a little cube over here, x, y, and z axes labeled for us, and we're taking a look at the deformation of this unit cube under multi-axial loading. So if we can see up here in the top, we have the unloaded cube, and down here in B, we have the deformed cube with multi-axial loading. So you can see we have all these loads acting at it right here in different directions. So we have here is this element subjected to this multi-axial loading. The normal strain components resulting from the stress components may be determined by using what we're going to call here, referring to as the principle of superposition. Now, this is going to require a few things. What it's going to require is that each effect is going to be linearly related to the load that it produces, and two, that the deformation resulting from any given load is small and does not affect the conditions of applications of the other loads. This is the assumptions that we're going to make. This is the requirements in order to use this principle of superposition. So it's going to have these restrictions listed down here by these relationships. We can see here our deformation in our x direction. Here's our x direction right here is going to be equal to positive. We have our stress in the x direction divided by our elastic modulus minus Poisson's ratio nu times the stress in the y direction divided by elastic modulus minus again over here our Poisson's ratio times the stress in the z direction divided by our elastic modulus. So that's how we're going to calculate our deformation in our x direction. We can go back over here. You can see here is our stress in our y, stress in our x, and stress in our z, all corresponding to our coordinate system that we have shown here. So this is another really great reason why you want to have your coordinate system drawn out, especially when you're talking about 3 dimensions, but even 1D and 2D, having these labeled, knowing which axis is which, and knowing what's positive and what's negative according to your chosen axes. So we have similar relationships we can see here, so that we see the correspondence we're talking about our epsilon y. You can see the y direction here is going to be the positive one without our Poisson's ratio, and the same with the z direction here for epsilon z. It's going to be our z direction here. That's just our sigma z over e. The other ones are both going to be negative in the other two directions times Poisson's ratio. So we saw that is the corresponding relationship between x, y, and z directions for our epsilon values. So we're going to continue on with the same unit cube here. So we have the same figure 2.33. We have the deformation of a unit cube under multi-axial loading, where the top here, A, is the unloaded, and bound here in B is the deformed shape of that cube. So we're going to look at now the dilatation bulk modulus here. So relative to the unstressed state up here, the change in volume, our E value for the change in volume here, is equal to Poisson's ratio minus 1. And we plug in for this, we end up with this relationship here of 1 plus, now we have epsilon x plus epsilon y plus epsilon z minus 1. So we can see the plus 1 and the minus 1 are going to cancel this relationship here, just leaving our E equal to epsilon x plus epsilon y plus epsilon z. Now we plug in for a relationship from seen on the previous slides earlier in this lecture. We can plug in now relative to our stress states here. So this ends up being, when we pull out our constant here for each of the x, y, and z components, we have the common factors here that we can pull out of 1 minus 2 nu Poisson's ratio, all divided by our modulus of elasticity times epsilon x plus epsilon y plus epsilon z. This is our dilatation, or our change in volume per unit volume. Now, for an element subjected to uniform hydrostatic pressure, we have this relationship here now where E is equal to the negative 3 times 1 minus 2 times Poisson's ratio, all divided by the modulus of elasticity times the pressure here. And we can see there is a relationship here, an inverse relationship between K and this 3 times 1 minus 2 nu all over E is the inverse of K here. And that's because K is our bulk modulus, or modulus of compression, which is equal to E over 3 times 1 minus 2 times Poisson's ratio there. So we can plug that in. We're up now that E is just equal to negative P over K. Now, another thing to note right now is that if this is subjected to a uniform pressure, the dilatation must be negative. Therefore, we have this relationship down here that our Poisson's ratio is going to be greater than 0, but less than 1/2. Now, throughout this course, we're going to talk about a couple different types of strains. So right now, let's talk about shearing strain. So we can see in our diagrams over here on the left-hand side in figure 2.36, we have a unit cubic element subjected to a shearing stress right here. So we can see our tau xy, our tau yx, our tau xy, and our tau yx right here on all these sides of the cube right there. So a cubic element is going to be subjected only to shearing stress, and it's going to deform into a rhomboid. So if that's the case where it's only shearing stress that's subjected to, it's going to take on the shape of a rhomboid. So the corresponding shearing strain is then going to be quantified in terms of the change in angle between the sides. So it's just going to kind of shear and change the shape that direction right there. We can look at it by the change in angle between the different sides. So now we have this relationship that we see right here. So now we go down to figure 2.37, kind of see what this looks like, and we say, okay, that's our angle right there. So this is going to be pi over 2 plus our angle in the xy direction. You can see there's still our shearing stresses right there on both of those sides there. And then you can see how this angle actually plays in. So you have all these different angles. You have these two angles and these two angles right here, all denoted separately like that. So these two angles on these two sides correspond to this relationship, and the angles on these two sides over here, in between those two sides, correspond to this relationship here. So it's pi over 2 minus our angle between an xy, and pi over 2 plus that angle right there. So that gives us those relationships that we're going to plug in for these guys over here. So a plot of the shearing stress versus the shearing strain is similar to the previous plots of normal stress versus normal strain, except that the strength values are approximately going to be half of that. So for values of shearing strain that do not exceed the proportional limit, we now have this relationship down here. So this is how we relate between those there, where G is going to be the modulus of rigidity, or our shear modulus is another way that we're going to call that. So let's apply this to a conceptual application here. So what we can see in this figure up above here, we have a rectangular block under that's going to be loaded in shear. So we can see this top load right here, our load P right here. So we can see that this is loaded in shear. It's rigidly connected down here to this tabletop or platform there. We have given dimensions. We know their overall length is 8 inches. We can see our width is 2.5 inches, and our height here is 2 inches. So I'd like to look at our diagram first before I even jump into the problem statement typically for a lot of these problems. So that's what I've done there, kind of got an idea of what's going on. So then I have a little bit better understanding when I'm reading through the actual problem statement, how to relate it back to the actual diagram. So down here in the problem statement, they tell us we have a rectangular block of material. So they don't tell us exactly what it is, they tell us the material, but they tell us that the modulus rigidity of that material is given to us as G is equal to 90 KSI. So that's something we want to write down in our given section for this problem here. Now this is going to be bonded to 2 rigid horizontal plates. So we can see that this material inside here is bonded to these 2 horizontal plates right there. The lower plate is going to be fixed. So we can see that this lower plate right here is going to be fixed to the surface. We know that's rigid right there. It's not moving. It's fixed right to that surface there. While the upper plate is what's going to be subjected to that horizontal force P. So there's that horizontal force P. So this is not moving down here. This is rigidly held in spot there. And then we have the shear force P up here pulling that across in that direction. So knowing that the upper plate moves through 0.4 inches, they give us that distance right there under the action of the force. They want us then to determine, so they're telling us what they're looking for, what they're asking for here. They want 2 different things that they're asking for. In part A, they want us to determine the average shearing strain in the material, and in part B, they want us to find the force P exerted on the plate. So we need to find our shearing strain and our force P that's going to be exerted on the plate. So your next step, if you're writing this problem out, you'd write down exactly in the form that I've talked about in the homework there. You have your name, what the date is, what homework problem this is, or what example problem this is. Then you're going to have a redrawing of your initial diagram over here, what all the givens are, whether it's the stuff that's given in the actual diagram or in the problem statement down here. All this listed out nice and neat, orderly there. And then you have a section of find. What are they asking you to find? Well, they're asking you to find 2 things. You're going to find A, the shearing strain, and B, the force P. So all that needs to be neatly written out in the format that I've discussed for the homeworks. From there, you can look back and reference that in a nice, easy spot rather than have to read back through all of this here before you begin your solution. Now, for the solution, what we're going to solve this in different steps. So the first step we're going to do is determine the average angular deformation or the shearing strain of the block, which we talked about in the previous couple slides. Then we're going to find our governing equation. What's our governing equation going to be? We're going to apply Hooke's law for shearing stress and strain to find the corresponding shearing stresses. And then from there, we're going to use the definition of shearing stress to find the force P. So this is kind of our plan of attack for how we're going to solve this problem. Now with this, we have all the information that's given to us. We know what they're asking us to solve for. We know what governing equations we're going to use there. So we have everything we need to begin the solution to this problem. So continuing on with our solution to this here, now we have this figure 2.41b. Now what's shown in this figure is the deformed block, which shows the shear strain. So we look up here, let's take a look at everything that we have. So we have this bottom plate here that's fixed to the surface, that goes from A to B. We have the top plate here, which is moving, and we have this load applied P here, and this is from D to E on these sides here. Now what we can see is we have this coordinate system defined, Z coming out this way, X going along this way, Y coming straight up there. And what we have here now is we can see we have this deformation. How much is this block moving forward, this top plate moving forward? Well, that's given to us as 0.04 inches. It's moving forward there. So we can see F goes from being in line with C right here on the Y-axis and moving forward that distance of 0.04 inches, which then gives us this angle, our gamma XY down here. So we can see we have our two distances here. So we know from our source right here, we know what those distances are, and we can then plug in and do a little bit of trig. So to determine the average angular deformation or the shearing strain of the block, we can say that our gamma xy, we do what our trig here, is the tangent here of gamma xy right there, and that is, when we look at our trig, 0.04, this distance over here, divided by 2 inches there, and we do that math out, we end up with gamma xy is equal to 0.20 radians. So again, pay attention to what units we're in. Are we in degrees or radians? We're going to stick with radians here. So from there, now that we have a value for our shearing strain of the block right there, our gamma xy, we can apply Hooke's law for shearing stress and strain to find the corresponding shearing stress. So we want to solve for this shearing stress right here, our tau xy. Well, we were given our modulus of rigidity here, which was 90 times 10 to the third PSIs, and this is giving in the problem statement. So again, that's great to have that first page to reference back to. We have all of your givens listed out, and exactly what you're trying to find in the end. So now we have that G that we can plug right into here to this relationship here from Hooke's law, times now the value for our gamma XY from up above, our shearing strain right there that we found is 0.02 radians. Plug these together, plug and chug. What we end up with is our tau XY, or our shearing stress here is 1800 PSI. So now using the definition for shearing stress, we can then back out and find our force P. So our pressure is equal to, when we rearrange it, our shearing stress times A, or what we saw before, our shearing stress is equal to pressure over our area. So if we move the A over there and multiply our area by our tau XY there, we can get our load. So we can plug in, well, we have our tau XY that we just solved for above right here, 1800 PSI. Our area we can calculate from the dimensions they gave us in the initial diagram. So that's, again, why it's great to have those there. So we have our length of 8 inches here, and we have our width of 2.5, so that cross-sectional area there is 8 times 2.5. Double check your units. We have inches squared, PSI, perfect. We end up with that, canceling that out. Pounds per square, inches squared, canceled with this squared inches on the top, so we're just left with our pounds right there. So our load is going to be 36 times 10 to the third pounds, or 36 kips. So from that relationship there, using Hooke's law, we were able to find our p-value. So next I want to take a look at the relationship between our modulus of elasticity, E, Poisson's ratio, nu, and our modulus of rigidity, G. And in order to do that, we're going to take a look at these diagrams over here. So in the top part, in part A of figure 2.42, we have representation of the strain of an axially loaded bar. In top A, we have the cubic strain element faces aligned with the coordinate axis. So you can see these guys are all here aligned with the coordinate axis, whereas in part B, they're going to be at 45 degrees to the coordinate axis down here. And we have our angles given by this relationship to gamma down there. So using those as a representation, we have this axial loaded slender bar. So if we think about this here, it's going to elongate in the x direction and contract in both the y and z directions. Let's go back over to part A here. So if I pull on this slender bar here in both these directions, P and P prime there, along the x-axis, it's going to elongate along that x-axis there. And when it does that, it's going to force it to contract along our y and our z-axes there. So that makes sense. So then we can take a look now at the cube on the inside of this. So initially this cube element is square shaped there. It's going to deform into rectangular shape. So if we look at this, if we start with the dotted line here of this cube in the center there, and then we move along and we pull our P and our P prime out like that, we can see it's going to change shapes into what we see here. So rather than having this shape of 1 and 1 there, this is now going to have two different shapes here that we can see. This now the height of this in the y direction is going to be 1 minus nu times our epsilon x, and in our x direction here, this was a 1 is now going to be 1 plus the deformation in the x direction. So that's all it's saying. This is going to be 1 plus deformation in the x direction. This is going to be 1 minus our Poisson's ratio times our deformation in the x direction there. So this is going to be less than 1. This is going to be greater than 1. This all makes sense. This is something that you really want to do when you're applying these relationships and equations. Go back to your diagram. Physically move it as it says it's going to move within the problem statement and make sure that everything makes sense. Now, if you're talking about this contracting in the y direction, all of a sudden this was going to be bigger than 1, bigger than it was initial value. If there's something wrong, you need to go back and think about that. Now we come down and do the same type of thing with the figure B here. So we had this cubic element in the center at 45 degrees. Now if we think about pulling this along the x-axis here in the P prime direction like that, what's going to happen to that there? Well, now we can see that this kind of moves out like this. Can change into this rhomboid shape down here where it becomes longer in one direction and narrower in the other direction right there. And it's going to change those angles. So the angles were before going to be just our gamma. We can see now the top one is going to be bigger than gamma, and this one is going to be smaller right here. So we have this relationship right there. So we can see, again, double check that. Does the angle get bigger on the top side up here between those two? And does it get smaller down here than the initial 45 degrees, initial 90 degrees in between those angles that they originally were? So we come down here, this gives us these equations now. So the components for normal and shear strain are going to be related by this following relationship as we've seen in this diagram if we've physically moved these. that our epsilon, or our modulus of elasticity divided by 2 times our G value there is going to be equal to 1 plus our Poisson's ratio, or we can rearrange this and solve for our modulus of rigidity here, which is equal to our modulus of elasticity divided by 2 times 1 plus our Poisson's ratio, so we can get this relationship there. And this can be rearranged based upon what we're solving for and what we have given to us, what we've solved for within our problems. So up to this point, we've kind of talked about uniform materials for the most part. So let's get into a little bit of what happens if we have some composite materials here. So let's just talk about a very common composite here. So we have a fiber reinforced composite material. And these are going to be fabricated by embedding fibers of a strong steel material into a weaker or softer material called a matrix. This is used in many applications. Oftentimes we see this in a practical application is the cores of snowboards. Oftentimes we'll have a fiberglass weave laid out over the top of them to create a composite material to make it a little bit stronger. So again, it's to make a material that's maybe lighter weight but weaker, but you want to add some rigidity to it, make it a little bit stronger, so you can add in some of this fiber reinforced composite material. Now, we've seen before that normal stresses and strains are going to be related by Hooke's law, but with directionally independent moduli of elasticity, we have this relationship down here now that we've seen before. Again, this is going to be dependent upon three-dimensional here. So our modulus of elasticity in the x direction, we can relate to our strain our stress divided by strain in the x. Same for y is stress over strain in the y direction, and the z direction for the z direction as well. Now for transverse contractions, these are going to be related by directionally dependent values of Poisson's ratio. So we have these relationships shown down here. So we have our Poisson's ratio in our xy direction is going to be equal to the ratio between, the negative ratio between epsilon y over epsilon x. Now for our Poisson's ratio xz, this is the negative ratio between epsilon z and epsilon x right there, where x, again, is the direction that the loads are moving in. Our axial loads are going along that direction in the x direction. So the three components of strain for all three directions, x, y, and z, are epsilon x, epsilon y, and epsilon z. Now for orthotropic materials, can be expressed in terms of normal stress only and do not depend upon the shearing stress. So now let's take a look at the sample problem here, 2.5. So in the sample problem here, we have this given diagram over here with some dimensions and a coordinate system x, y, and z in 3D. So what we tell us in the problem statement for this here is we have a circle of diameter given to us as 9 inches is going to be scribed on an unstressed aluminum plate with a known thickness of T is equal to 3/4 of an inch. So we can come back over here. Well, we have now that we know that we have a plate over here. We know it's made of aluminum. We can see our scribed circle in the center of the plate there. We have 15 inches, so we know the dimensions of this here. And we know that the thickness of this plate here is going to be 3/4 of an inch. And they tell us there's forces acting in the plane of the plate. They're going to cause some normal stresses, sigma x and sigma z. So we have our sigma x acting in our x direction here and sigma z acting right here. And we can see all those loads right here that are going to be causing those stresses. Now, if they give us a modulus of elasticity for this material here, this aluminum, they tell us that our modulus of elasticity is 10 times 10 to the negative 6 psi. Now, this is something that's great. They gave us that modulus of elasticity in the problem because they really only told us aluminum. They didn't tell us what type of aluminum. There may be times that they tell you a certain type of aluminum and you need to go to the tables and actually look up and get this information. But for the simplicity's sake, they gave it to us in this problem here. They also gave us Poisson's ratio here of 1/3. So they give us a lot of information in the problem statement and the given diagram here that, again, we want to write down in a neat, organized manner. Here's my givens. Here's my initial diagram simplified down, everything I know, the correct units. And then what we're looking for would be the next section in our write-up here. They want us to determine 4 different things. They want us to determine the change in the length of diameter AB. So there's from A to B as this stretches. The change in length of diameter CD, so going in this direction right here, in the Z direction, C and D right there. The thickness of the plate, what is the change in the thickness of the plate, and what is the change in the volume of the plate. So we have A, B, C, and D, 4 different things that we're going to need to solve for within this problem. So as we continue on with our solution to the problem, the next step is to look back at all the givens that we've written down, everything they're asking us to solve for, the initial diagram, and from there, come up with what are our governing equations. How do we begin the solution? What's our key equations that we're going to utilize? Well, one of the key equations we're going to utilize in the solution is the generalized Hooke's law. And what we're going to do is we're going to use this to find the 3 components of our normal strain. So let's try it for our x direction first. We always want to break things down, especially when we're doing in multiple dimensions or a 3D problem like this, into individual components here. Let's just take a look at the x first right here. So if we're looking at our normal strain in the x direction, we have this relationship that we've developed before here. So we can take for our normal strain in the x direction, we have this relationship that we have our positive stress in the x direction is sigma x divided by our modulus elasticity minus Poisson's ratio times our sigma y, our stress in our y direction, divided by our modulus elasticity, minus Poisson's ratio times our sigma z, stress in the z direction, divided by modulus elasticity. So now it's great that we have that first page all set up for us. We can go back, plug and chug right through this, and we can see, okay, well, I have my modulus elasticity that I can pull out front here, my 1 over e. Here's my e, 10 times 10 to the positive 6 units of psi right here, times right here. Now we can go through all of this, and we have our sigma x on the top right here, 12 KSI. We have now over here all of our other information that we can plug back in for our Poisson's ratio and our sigma y and sigma z. So we plug those values in there. So this becomes 0 because there was no sigma y there. Then we can move, that term goes away. So now we're just left with our Poisson's ratio times our sigma in the z direction. Our sigma in the z direction was given to us as 20 KSI, and our Poisson's ratio was given to us as 1/3. So this now simplifies down. We plug and chug this right here. We end up with our sigma x is equal to positive 0.533 times 10 to the negative third, and make sure your units are correct with this here. For that, so then we plug in, we go on to our next relationship. So here's our governing equations here from generalized Hooke's law, and we can utilize this here that in the y direction, our sigma y right here, epsilon y right here is equal to our negative Poisson's ratio times sigma x over epsilon, so on and so forth, same here, sigma y over e, then minus nu times sigma z over e for our modulus elasticity again. We can go through the same thing, pull out our epsilon, or our modulus elasticity out front of everything here, plug in our known values here, and again, recall what things drop away, what things we have actual values for. So our new value for Poisson's ratio was given to us as 1/3. We had values for our sigma x here that we could plug in as 12 KSI. We have values for our sigma z here that we can plug in as 20 KSI. We do that out, plug and chug, and we end up with our epsilon in the y direction is given by this relationship here. Negative, we can see now here from the values here, because our positive goes to 0. These are both negative values there. So we have a negative 1.06 times 10 to the negative third. Then we do the same thing for z, plug in those same values, pull out of our modulus elasticity out front, plug in our known values for sigma z, our sigma x, and our Poisson's ratio, and we end up here for epsilon z is equal to 1.6 times 10 to the negative third there. So now we have all the components x, y, and z for our normal strain. Next, what we want to do is evaluate the deformation components. So we recall the relationship that deformation is equal to epsilon times our d value right there. So d is our diameter right there of that circle. So we can say, okay, if this deforms, it originally had a diameter of 9, we want to see how much it deforms by. We have how much it deforms by right here. We have this value here for each direction, our x, y, and z, and we see that we're only concerned with our x and z direction is what it asked for the deformation of that. So we have our original value there multiplied by that value we found for our normal strain there, and that'll give us our deformation for each of those there. So what we can do is we can come up with and see for our deformation for BA and our deformation for CD over here, and we do that off of that initial value of the 9-inch diameter. So we see that this guy deforms in the AB direction there by 4.8 times 10 to the negative third inch, and in the CD direction it deforms by 14.4 times 10 to the negative third inch there. So we can see how that changes based upon based upon the initial diameter of that there and those initial loads that were applied to it. So that was two of the things they asked us to solve for in the solution to this problem. The next thing they said is, how does the thickness change? So if we think about this for a second, we're pulling this in those two directions there, and in both directions that diameter of that scribed circle is getting bigger. What do we think is going to happen to the thickness of that plate? So if two of the dimensions are increasing, what is going to happen to the dimension of the thickness there, the other distance that they asked us to solve for? So we can plug that in there. We can see this relationship here, that the deformation there is going to be equal to the initial thickness times that epsilon in the y direction. We have that epsilon in the y direction that we see right there, so we can plug that guy in right there times that initial 3/4 inch thick, and what we see is this does decrease just as we expect it to right there by 0.8 times negative third inches. So now we want to find that change in volume was part D that they asked us to solve for there. For that change in volume, we now can utilize this equation that we saw earlier, that change in the volume there, E, is equal to epsilon x plus epsilon y plus epsilon z. We do that there, and we find out that this is equal to now 1.067 times 10 to the negative third. And we plug this into this relationship here for change in volume right there, because there's a unit volume there times the original volume of this guy there, because this was a change in unit volume right here for E. Multiply that change in unit volume by the original volume. So the original volume, we take those original dimensions of 15, 15, and 0.75, and then that becomes our initial volume times our change in volume there. So we see we have an increase in volume or change in volume here of 187 inches cubed. So continuing on, what I want to discuss next is St. Venant's principle. So before we get into what this is, I want to talk about a couple of different types of loading. So we have here, when loads are transmitted through a rigid plate, they're going to result in uniform distribution of stress and strain. And we can see that over here in A and B, where you have this axial load applied to these rigid plates on the top and bottom right here to a rubber model. So we have from that, this results in, again, that uniform distribution of stress and strain. Now for concentrated loads, these are going to result in large stresses in the vicinity of the area where the load of application point is. So we can see this over here in this figure 2.48. We have this concentrated axial load coming in right here to that same rubber model right there. And now you can see the large stresses that are going to occur in the vicinity of where those point loads are. The other thing to think about here is that the stress and strain distributions become relatively uniform, and you're talking about these short distances from the load application points. So what St. Venant's principle says here is that these stress distributions may be assumed independent of the mode of the load application, except in the immediate vicinity of the load application points. So we can see down here in 2.49, we have the diagram here, and if this width right here, where the two loads of this object for the two loads are applied, P and P prime there, if this distance here, this length right here, is equal to the width right here, we see these are relatively uniform right there. So our stress min and stress max aren't too much different from each other. But now if we drop this down to being half that width, half that thickness as the width is there, then we start to see a little bit of discrepancy and difference between our max and our min stresses right there. So you kind of see it takes on a little bit more of this shape here. And then if we drop that down half again, so it's a quarter, the thickness is a quarter of that width right there for that applied load over there. Now we see quite a bit of difference between our min and our max right there, and we can see the shape right here, and we can see how we have our stress average is going to be equal to our load over area right there, but here's our stress min and here's our stress max right there. So we can see how the geometry of this is going to definitely affect this. So I'm going to continue on and talk about stress concentrations. So particularly right now, we're going to take a look at the stress concentration for a hole. So we'll take the simple case here. We see in figure 2.50 here that we have stress distribution near a circular hole. So we can keep it a nice simple circular hole, and it's going to be a flat bar just under plane axial loading here. So we have this flat bar up here under plane axial loading. You see your P and P prime right there putting under axial loading. You can see the dimension here for the width of this is given by D. We have our dimension here showing us the distance from the edge of the bar to the beginning of the circle there. We can see the circle has a radius R right there. So we have all the geometry and dimensions defined for us in the diagram there. So what we can see now is we have these stress concentration factors. So this is defined as the variable K, where K is equal to our sigma max, our max stress, over our average stress right here. So if we go up to the bottom part of this diagram up here, what we can see is as we move from the edge of the hole in towards the center where we've come up with the edge of the bar in towards the center where we start touching up with the hole right here, we can see that our stress is going to be increasing right there. Now this dotted line down the center right here is our average stress right here. We can see here's our minimum right there on the edge. Here's our max as we get up right touching the edge of that hole there. And these are the two values that we'll be using to find the stress concentration factor, K, right there, where we have our sigma max right here, divided by our average stress right there, sigma average right there. Now for this particular case here, for a flat bar with holes, we have this graph shown here for figure 2.52a, which is the stress concentration factors for flat bars under axial loading. For this very particular case, we have this relationship here where we can start off, we can see on the bottom here our dimensions right here, where this is 2 times r divided by d, where r is your radius of the circle up here, and d is the width of our bar right there. So as this increases from 0 all the way out here to 0.7, we can see what happens is right at 0, when with this ratio here, we start at 3, and this slowly decreases down in a nonlinear fashion right here until we get out to 0.7, where it gets down to just a little bit over of a stress concentration value K of just over 2. So the thing to think about is this ratio here and what this means in terms of our actual bar with a hole in it here. So if this value for this ratio of 2 times the radius or the diameter of our hole divided by the d value here, for this to increase, that means the numerator needs to increase. And for the numerator to increase, that means that this hole is getting bigger. So as the hole gets bigger here, relative to the dimension d here for the width of the bar, that is going to cause our K value, our stress case concentration value right over there, to decrease. So note down here, discontinuities in the cross section may result in high localized or concentrated stresses. So the next thing we really want to focus on here is stress concentrations using a fillet. Now where this is important in a practical application is when you're talking about a dog bone specimen in a tensile test here. So it's really crucial to kind of figure out what we need to make this radius relative to the dimensions of our dog bone specimen. So this is a really great resource to have to reference back to as you're talking about maybe getting into some of your ME124 labs, or if you're doing any material testing where you're doing some tensile tests and you use some dog bone specimens, that radius quickly becomes important. And we didn't really discuss that too much before when we talked about tension testing there. We're really talking about that cross-sectional area, based on this D value right here. What we really want now is think about the stress concentration factor right there, because when we're doing a dog bone specimen, we don't want this to be our highest stress concentration up here, right there. We don't want this to be the area that fails. We want to minimize that there and make the area that fails down here at this minimal cross-section area of the dog bone specimen. So we have this ratio here. We have the width of the head here, and we have the width of our cross-sectional area of the specimen right there. And then we have our radius of our fillet over here. Then we can see we're pulling this in tension. So there's our loads right there. And what we can see from the bottom part of this diagram here, and again, this shows the stress distribution near fillets of a flat bar axial loading. We have, as we come out towards the edge of this fillet here, our max stress right out here, and we can see our average stress right there. So now we can see we have this ratio for R over D, which is the ratio of our radius over this dimension of the center section of our dog bone specimen right there, D like that. So if we take a look at that there and we say, okay, what does this mean as far as our stress concentration? So our stress concentration factor for flat bars under axial loading, we can see as this ratio increases from 0 right here all the way up to 0.3 in this graph here, we can take a look at how that changes our K value, also considering the ratio between the head size and the thickness here. So we have, between our ratio of our head size and thickness here, our big D over little d, we can start out with 2 all the way down to 1.1 there, and how does that affect? And this is something great to reference back to figure out how do we minimize, or what do we get the desired stress concentration factor right here when we're setting up our specimens. So let's take a look again at that same example with that flat steel bar under axial loading here. We're looking at this fillet here as well. So let's do a problem utilizing this here. Now in this problem here, we can see we have that head width there as capital D, and we have the thickness of the cross-sectional area of this dog bone specimen down here as D, and we have this fillet right here of R, and we can see it's under axial loading P prime right there. Now what they're asking us to do in this problem is to determine the largest axial load P, so we need to find out what this P value is here, that can be safely supported by a flat steel bar consisting of 2 portions, both 10 millimeters thick and respectively 40 and 60 millimeters wide, connected by fillets of radius equal to 8 millimeters. So within that statement there, they give us all the dimensions that we're going to need in order to solve the problem. They also tell us to assume an allowable normal stress of 165 megapascals right there. So that's going to be important for some of the calculations we need to do. Now that we have all this information given to us, they know what we're asking us to solve for. We're trying to find that load, that max, the largest axial load P. We have all the dimensions. We know it's 10 millimeters thick. We have the dimensions of 40 and 60 millimeters wide right there. And we know we have a radius of 8 millimeters. So we need to use all that information in order to calculate that axial load P, assuming that we don't have an allowable stress any more than 165 megapascals. So in order to do this, we begin our solution. Take a look at all the given information, what they ask us to solve for. We want to determine first the geometric ratios and find the stress concentration factor, our K value, from our figure 2.52. Now next we want to find the allowable average normal stress using the material allowable normal stress and the stress concentration factor K. And last we're going to apply the definition for normal stress to find the allowable load, which is what we're looking for there. Our allowable load is P. So we take a look over here, continue on with our solution, and what we want to do is we go back to that graph we looked at earlier here, so we can back out our stress concentration value K based off the R over D ratio there for our particular sample. So that's what we do there. First we want to determine the geometric ratios and find the stress concentration factor from that figure that we see there. So we have our big D was given to us as 60 millimeters right there. Our little d is given to us as 40 millimeters right there. So that ratio, regardless of units here, normally I'd say make sure we get out of millimeters going to meters, but they're going to cancel out for a ratio here. So we have a D over D of 1.5. Now we have an R over D, this R value here for our fillet there is given to us as 8 millimeters, and this is going to be our D value right here, which is still that 40 millimeters right there. So this little D right here is our 40 millimeters right there, and that ratio is at 0.2. Again, millimeters cancel out. This is unitless, just as the ratio there. So now, from this first ratio, our big D over little d, we can tell us what curve we're on. This is 1.5. There's 1.5 right there. So we can follow this down and find out we're on this curve right here. Our R over D gives us 0.2, so we can come down here to 0.2, so we can go follow our 0.2 all the way up until we intersect with that 1.5 curve right there. From that right there, we can see we're just about there. We come all the way across over here, and what we see is we're right here of our K value when we draw that line straight across there, 1.82, and we come across, if we were to actually use a ruler and do that correctly, we're just above 1.8 where that intersects right there. So we see that now our stress concentration value, our K value right here, from that figure 2.52 is a value of 1.82. And we got that from all of our dimensions, our geometric information they gave us in our problem statement for this bar. So now from there, what we can do is find the allowable average normal stress using the material allowable normal stress and the stress concentration factors. We just solved for that stress concentration factor right there. So we have our K value right there. Now they already told us in the problem statement that our sigma max right here is at 165. So we have this relationship here. We can say the sigma average is equal to our sigma max over our K value, plug in our known values there, 165 megapascals divided by 1.82 gives us our sigma average here of 90.7 megapascals. So this is our allowable average normal shear stress. From there, we can apply the definition of normal stress in order to find our allowable load. So we have here that our load here is equal to our cross-sectional area times our average stress that we just found, our allowable average normal stress up there. We just found from this right here. So we can plug that value in right there for our average normal stress. What is our cross-sectional area? Well, the thickness of that bar times the width of it is 10 millimeters times, 10 millimeters times our 40 millimeters right there. Make sure we convert to the correct units when we plug this in here of meters rather than millimeters. And we find out here that maximum, or that load that we're looking for here, our allowable load, is P is equal to 36.3 kilonewtons. So a pretty straightforward problem just from our dimensions and the geometry that they gave us there. Able to go back to figure 2.52, plug in those ratios, go up on the curve, find out what curve we're on, come over, get our stress concentration value K there, plug that in order to find that load. So next I want to talk about elastoplastic materials here. So we have the special case here. You can see over here in figure 2.53 where we have a stress strain diagram for an idealized elastoplastic material. So for this case here, based on our previous analysis on the assumption of linear stress strain relationship, example, stresses below the yield stress right here. So there's our yield stress right there. So for stresses below the yield stress there. So the assumption is good for brittle materials which rupture without yielding. Now, if the yield stress of a ductile material is exceeded, then plastic deformation is going to occur. So analysis of plastic deformations is simplified by assuming an idealized elastoplastic material. So these deformations of this elastoplastic material are divided into the elastic and plastic ranges. So the permanent deformations result from loading beyond that yield stress. So that's what we're talking about here. If you think about this here, we come back over this diagram now. If we stay under our yield stress right here, it's perfectly elastic, perfect linear region here. So theoretically, if we load this and don't go above that yield stress right there, it should return down to that same position and have no strain, no deformation at all. It'll have the same original length. So we pull that up, stay in the elastic region, release it, unload it. Goes back to the same exact dimensions as it had initially, no length changes at all. But if we exceed now our yield stress right here, our sigma sub y, and then all of a sudden we go into our plastic range, and you're going to start seeing these permanent deformations. So once we get to this point here on y, we start seeing these permanent deformations. So then, even if we go all the way to c here and we unload it at this point here, when we passed that sigma y value there, we'll see as we'll go back now to this new position D on our strain curve. So that's where you have these permanent deformations. So even after you've unloaded it, it's now longer, it's now deformed, it's got increased in length. So that then leads us into plastic deformations. So again, we review here elastic deformation while the maximum stress is going to be less than that yield stress. So we'll stay in that elastic region as long as our max stress does not exceed that yield stress. So we can see that in part A of our diagram right here, where this diagram shows the distribution of stresses along the elastoplastic material under increasing load. So we put that load there and we can see our sigma max, or our maximum stress right here, is less than our yield stress. There's our yield stress right there. So if that stays less than that, we can see we have this relationship here that our load is equal to our sigma average times our cross-sectional average area right there, or we can plug in for this guy here with our K value there for our stress concentration, and we end up with this relationship shown here. So now we go to our next case here where we can see that our sigma max is equal to our yield stress there. So then we have this relationship right here, that P sub y, our load at yield right there, is equal to our sigma y times our area divided by our K, our stress concentration factor there. So this says our max stress is equal to the yield stress at the maximum elastic loading. So now, when the loadings are above the maximum elastic load, a region of plastic deformations develop near that center hole. Now, what's going to happen here, if we keep increasing the loading, as that loading increases, the plastic region is going to expand until the section is at a uniform stress equal to the yield stress there. And that's what we see down here in D, where we have the average stress is equal to the yield stress right there. And you can see this is represented, all those lines are now equal to each other across there. And now we have this relationship here that our P sub U is equal to our sigma Y times A, or plugging in here, our stress concentration factor K times P y, where our Py is plugged in from this relationship up here. So now I want to talk about residual stresses. So as we've seen here, when a single structural element is loaded uniformly and it goes beyond its yield stress and then unloaded, we can see then that it's going to be permanently deformed, but all the stresses disappear. Now, it should not be assumed that this is always going to be the case. So residual stresses are what will remain in a structure after loading and unloading if the following criteria: only part of the structure undergoes plastic deformation, or different parts of the structure undergo different plastic deformations there. So in those cases there, these residual stresses will remain in the structure after loading and unloading has been performed. So these residual stresses can also result from uneven heating or cooling of structures or structural elements. So this is something to consider. Some of these parts are going to be heat tempered or cooled in a bath afterwards. So there may be residual stresses already in some of the parts you'll be using. So that's something to consider more along in the design process as well, are these residual stresses in your materials for the components of your design project going to be something that is going to be an issue. So that's something to think about when you're talking about tempering, heat treating, and cooling of parts.